Have you ever heard of how metals like sodium or chlorine are extracted? These aren't found freely in nature. We actually force them out using electricity. That process takes us right into the world of electrolytic cells. Unlike batteries that generate electricity, electrolytic cells work in the opposite direction. They consume electricity to make chemical reactions happen. These are called non-spontaneous reactions. In an electrolytic cell, you have two electrodes dipped in an electrolyte and connected to an external power source. The magic happens when electricity flows through the circuit. Here, the anode is positive and oxidation takes place there. The cathode is negative and reduction happens there, just like in galvanic cells, but with opposite polarity. The electrons are actually pushed from the external battery towards the cathode, making this setup ideal for processes like electrolysis of molten salts. For example, when we electrolyze molten sodium chloride, we get sodium metal at the cathode and chlorine gas at the anode, an industrially valuable process. Let's clear up a common confusion. How are galvanic cells different from electrolytic cells? Think of a galvanic cell as a chemical battery. It produces electricity from a spontaneous reaction. An electrolytic cell is the reverse. It needs electrical energy to make the reaction happen. In galvanic cells, the anode is negative and the cathode is positive. But in electrolytic cells, it's flipped. The anode is positive and the cathode is negative. Another distinction is their structure. Galvanic cells used to separate half cells connected by a salt bridge. Electrolytic cells can operate in a single container with electrodes immersed in a molten or aqueous electrolyte. The flow of electrons is also externally driven in electrolytic cells. And as we'll soon see, this forced flow gives us the power to purify metals, electroplate surfaces, and even generate clean fuels like hydrogen. So how does electrolysis actually work? When we pass a direct current through an electrolytic solution or molten compound, positive ions or cations move towards the cathode and negative ions or anions move towards the anode. At the cathode, cations gain electrons and get reduced. For example, copper ions, written as Cu2+, gain 2 electrons to form copper metal. The reaction is Cu2+ plus 2 electrons gives Cu. At the anode, anions lose electrons and get oxidized. For instance, chloride ions lose electrons to form chlorine gas. The Cl- gives Cl2 plus 2 electrons. To make this possible, the electrolyte must be either molten or aqueous, allowing free movement of ions. And the amount of chemical change that takes place? It follows a law, Faraday's law of electrolysis, which we'll explore shortly. Let's look at one of the most widely studied examples, the electrolysis of sodium chloride or common salt. When molten sodium chloride is electrolyzed, sodium ions move to the cathode and get reduced to sodium metal, while chloride ions go to the anode and are oxidized to chlorine gas. The net reaction is 2 sodium ions plus 2 chloride ions gives 2 sodium atoms and 1 molecule of chlorine gas. But in aqueous sodium chloride, it gets a bit trickier. Water also participates in the electrolysis. At the cathode, instead of sodium ions, water molecules get reduced, forming hydrogen gas. At the anode, chloride ions still get oxidized to chlorine gas. So, the final products of aqueous sodium chloride electrolysis are hydrogen gas, chlorine gas, and sodium hydroxide left in the solution, a process widely used in the chloralkali industry. Now comes the fun part. Where is electrolysis actually used? One major use is in metal extraction. For instance, aluminium is extracted by electrolyzing molten aluminium oxide in cryolite, a process called the Hall-Héroult process. We also have electroplating, where electrolysis deposits a thin layer of metal, like silver or gold, onto a surface, enhancing durability and appearance. Another powerful application is the electrolysis of water to generate hydrogen and oxygen gas, a sustainable step toward clean hydrogen fuel. The chloralkali process, used in industry, electrolyzes brine to yield chlorine, hydrogen, and sodium hydroxide, all crucial for detergents, PVC, and disinfectants. In short, electrolysis is the chemical workhorse of modern technology. So how do we predict how much substance is produced during electrolysis? That's where Faraday's laws come in. First law says the mass of substance deposited or liberated at an electrode is directly proportional to the amount of electricity passed. The formula is mass equals Z into Q, where Z is the electrochemical equivalent and Q is the total charge in coulombs. Second law states when the same amount of electricity is passed through different electrolytes, the mass of substances deposited is proportional to their equivalent weights. The equivalent weight is calculated as the atomic mass divided by the number of electrons involved in the redox process. Thanks to Faraday's laws, industries can now precisely control electrolysis to manufacture everything from circuit boards to car batteries. Let's quickly go over what we've explored today. We learned that electrolytic cells use electrical energy to force non-spontaneous reactions, quite the opposite of galvanic cells. Electrons are pushed from anode to cathode. Oxidation happens at the anode and reduction at the cathode, even though the anode is positive. In both molten and aqueous electrolysis, ions migrate to electrodes where redox reactions occur. Depending on the conditions, different products can form, like hydrogen gas, chlorine gas, or even sodium metal. Faraday's laws help us quantify electrolysis with precision, linking electricity to chemical yield. From metal extraction to hydrogen fuel, electrolysis is not just textbook chemistry, it powers the world. I hope this session helped you see how electricity and chemistry come together in fascinating ways. In the next class, we'll dive deeper into electrochemical applications like batteries and fuel cells. See you there.